Welcome back to another OpenGL GLSL tutorial, and this time we are going to replace the built-in matrix and all of the built-in matrix operation with a matrix which is not part of the OpenGL. Actually, we are not going to write a matrix class. I've thought about that maybe we should try to make one, but that will be just typing in a lot of matrices. So how do they look like? And I thought that maybe we should just try to use a matrix which is already finished, so we don't have to work that much about the matrices. Okay, so what we are going to replace is basically every operation which the matrix use: load identity, perspective, ortho, GL ortho, and GL translate, GL rotate, GL scale. So basically everything which deals with matrices in OpenGL. So you probably know by now that the matrices are the base of the 3D transformation. So matrices moves your vectors and objects where you want them. Matrices rotate them, scale them. So everything is done by matrices. And of course you know that because if you are here, you probably already followed the GLSL tutorial. So you remember that right here, for example, in the vertex shader, we are multiplying with this GL model view projection matrix, which basically put the vertices into our 2D screen, or GL normal matrix, which rotate the matrix, or GL model view matrix. So everything is done with matrix multiplication. But in the newest OpenGL, actually not the newest, but from OpenGL 3.2, I believe so, the built-in matrices no longer exist. You have to actually manually create a matrix. Now we could actually go into creating a class with 16 floating point variables and defining the operations. Some operations are quite trivial, like scaling. Basically, you just put numbers into the main diagonal, the x, y, z into the main diagonal. How much do you want to scale the object? Some are require more of a trigonometry, like rotation and mostly perspective projection. Perspective projection is quite complicated actually to put it into a matrix form. But we are not going to make that. I don't want to take your time with making such a class. Instead, we are going to use a class which is already ready, and actually it is used GLM. This is the OpenGL mathematics library right here. It doesn't actually just containing matrices, it's containing vectors, quaternions, and a bunch of useful stuff. We are only going to actually use the matrix from this class because it already have everything which you need basically for doing matrix math. So it already have the rotate, scale, translate function. We are just going to create a simple wrapper class around it, so the interface will be almost like if you are just using the built-in matrix. So you don't have to forget everything which you have learned so far about matrices. We are going to create a little wrapper class, and you can basically use the same function. So it will be just a simple replace. We replace the translate f function with the dot translate function. So that's all. So let's download it. I'm going to download the latest version right here. This is a simple zip file. So basically you don't even have to build it with CMake or Make. You just put it into your project and everything will work out. So right here I just downloaded it and opened it up, and actually we don't even need all of this. We only need this folder GLM. This is what the actual material of this library. So here are the codes. By the way, the license, if you are if you want to know the license of this program, it's pretty free. So you are free to modify, distribute, and pretty much everything which you will do with a free source software. So it's pretty cool. You don't have to worry about the licensing problem. So let me just put this GLM folder into our project folder right here, GLM. Pretty simple. And now we are ready to make a class. Actually, I created two new files, the matrices.cpp and matrices.h. This will contain the projection, model view, actually the model and the view matrix separately, so it's containing 3 matrix. I decided to separate the model view matrix into 2 separate matrix, the model matrix and the view matrix, because sometimes we need them separately. And getting the model matrix or the view matrix from the model view matrix is not that simple task. It's required to multiply by the inverse of the other matrix. Oops, where is my file? Right here. Right, so let's actually start. I will say this will be a relatively simple tutorial, so you don't have to really worry about getting lost, I think. Okay, so let's start. We are first starting with the inclusion guard as always. So matrices underscore age. Then we just define the matrices underscore age and put an end div, because probably a lot of file will include this matrices class, because everywhere we need to do this matrices stuff. Okay, what do we need to include? Probably we need an IO stream, just if we want to write out something. I usually include IO stream. We probably need, we maybe need a vector. Do we want to use pushback function? I'm not sure. I don't really use pushback function lately, but I guess it doesn't hurt if we have a pushback function. So I'm just going to include a vector. Right. Now we need the GLM, so this math library, which we have loaded all of the basic matrix function. So we need to include actually three kind of different headers. So this is one of them is glm/glm.hpp. This is basically including almost everything. The next is under glm/gtc, just little copying from somewhere, matrix underscore transform.hpp. And we have one last include and glm/gtx/transform.hpp. Okay, so this free header, if it is included, then you can pretty much use matrices as you would like to. You can actually take a look into these header files to see what kind of functions there are. It's a bit harder to read than a normal header file, because it's kind of optimized and it is using templates quite a lot, but it's not that hard. But you know, it's harder than read something like the simp header file. Okay, and I will also include the glee header file, so glee.h, because I'm going to make a member function which updates the matrices in the shader, and you know, we need the GL use program and stuff like that. Okay, so let me create the class matrices, and this matrices class will actually hold the free matrix which I have set. So I'm going to create a vector of matrices. So when we use pushback, so I'm going to make a member function pushback, and the pushback is pretty much doing the same thing as the GL pushback matrix. Was it GL push matrix, GL push matrix, and GL pop matrix? So GL push matrix pretty much done that. It puts the matrix into a stack. So we are just going to push another element into the vector. So in this way, we can do stuff like that. But if you don't want to use push matrix and pop matrix, what you can do is pretty much just create a simple matrix. Okay, the matrix 4, so the 4-dimensional matrix, 4x4 matrix, is actually defined in the GLM namespace called mat4. I don't advise to use something like using namespace GLM, because this mat4 is a kind of short name. So just to make sure you do not have some conflict with another library or another type or another variable name. Okay, and I call this model matrix. The next one will be almost the same, except this will be the view matrix. The view matrix pretty much will be only modified by the camera, and this is the object position. Right, and to get the model view matrix from the model matrix, so actually I write it down here, model view matrix, as you remember we use that, we are going to multiply the view matrix by the model matrix, so view matrix times the model matrix. When you're doing matrix math, it is important to remember to do everything in the opposite order. So we have model view matrix, then you multiply first by the view matrix and then the model matrix. If you have a model view projection matrix, then first start with the projection matrix, then the view matrix, and then the model matrix. So just a little bit of how it works. So do the multiplication in the opposite order. By the way, this is how we combine transformation together, by multiplying together matrices. I will not go into that how it's mathematically work. You only need to remember that it does work. Okay, and the last matrix, it will be again using a vector glm mat4, and I just call it projection matrix. Alright, and again, to get the GL model view projection matrix, GL model view projection matrix, you just have to multiply first by the projection matrix, then the view matrix, and then the model matrix, right there. Okay, and actually I'm going to make a member variable which defines what matrix I am currently using. So you remember we have a function GL matrix mode, and you can tell like GL projection and GL model view and GL. So we are going to make a variable, simple variable, which holds which matrix I am currently using. Okay, so I'm just going to make an integer, and I call this current matrix. I will not to optimize this class. I'm not afraid that this will slow our program down, because you mostly do translation, rotation, and scaling once per object, and I don't really think that it will really makes a huge lot of difference if I don't use this, but instead of using an array index. You will see what I mean in a moment. But let's first create an enumeration, and I just call it matrix modes. And this matrix mode will have the three possible values, which is either the model matrix, the view matrix, or the projection matrix. So we are later going to create a function matrix mode, and you just set one of these constant. You just pass one of these constant into it. So I'm just creating a model matrix variable equal to 0. The next one will be the view matrix variable, and the next one will be the projection matrix. Perfect. What I'm going to do is try to optimize a little bit. Whenever we used the shaders, you remembered that we have function, actually I close the shader, not function, member variable, or member variable, I don't know, building variable rather, model view matrix. If we don't have this variable, of course we can calculate it by, right here I wrote it, view matrix by model matrix. So if I write this to shader view matrix by model matrix, it will calculate the model matrix. If I write projection matrix, view matrix, model matrix, then it will calculate the model view matrix. But if you put it into the vertex shader, that will mean that it has to run every time. So this multiplication has to run every single vertex on the screen which you render. Now that could be possibly thousands of vertices, and of course it is quicker, because doing floating point calculation on the GPU is much quicker than doing floating point calculation on your CPU. But what I am actually going to do is calculate this model view matrix and model view projection matrix, and actually normal matrix as well. I will get into what normal matrix is in a moment on the CPU, and then pass this value, so the calculated model view matrix, model matrix, view matrix, model matrix, projection matrix, so everything passed separately as a matrix. So it will mean we have to only calculate it once on a slower device, opposite to possibly thousands of times in a quicker device. So which is the quicker, I don't know. It probably depends on how many vertex you have, but my idea is to calculate it on the CPU. So what I'm going to do is create 3 more member variable right here, glm mat4, and one will be the model view matrix. I create another mat4 object which will be the model view projection matrix right here, and I create a third one called the normal matrix. So mat3, it will be a 3-dimensional matrix, so 3x3 matrix. I will get into a moment what is this when we actually calculating it. And this one is called normal matrix. This one will replace the built-in GL_normal matrix on the shader. But we don't necessarily have to calculate this every time, so I'm just going to make a boolean variable called matrices ready. So this matrices ready will be true whenever it is already calculated a frame before, for example, and false if we did either scaling, rotating, or translating, or set the projection, because then we have to recalculate these matrices. So it's just a little optimization. So we don't have to calculate the model view matrix every time. If neither, we don't have to calculate the model view matrix if either the model view matrix, or if the model matrix and the view matrix not changed. So we only have to calculate if either the model or the view matrix have changed, basically. So optimizing the technique. Yeah, I'm pretty sure we have all the variables. So we are going to have a constructor, which is pretty much will be just an empty constructor, so no parameter. But of course we calculate these matrices, set everything to identity matrix, which is the matrix which doesn't change anything. Okay, we don't need the destructor because nothing is allocated dynamically. So let's start with the OpenGL function. We have a load identity function, which loading back the identity matrix, which is the no transformation. So it is equal to the GL load identity function, and this will load the current matrix equal. So it makes the current matrix equal to the identity matrix, which pretty much means that there is no transformation. No transformation. Okay, we need a matrix mode variable, so void matrix mode, and it's waiting an integer I, and this will be equal to the GL matrix mode, and just set this current matrix variable to whatever we specified here in the I. Now let's continue with the transformations. So transformation. What we will need is translate, and the translate with free variable parameters x, y, z, and this is equal to GL translate f. Let me put the equal sign here. Oops, that's not equal, that's equal. GL translate f, and this will exactly do the same thing. It will translate the current model or view matrix. The next is the scale. So void scale. I'm actually going to make two scale functions. One is scale function for the scaling, which is so it has different parameters for the different scaling. So this is equal to the GL scale function, scale f. Okay, and I'm going to make another scaling function, an overloaded one, which has only one variable, and it's scaling the object, so it's keeping it ratio. So it's the same as GL scale x, x, x. So all of the variables are the same here, x, y, z. It is useful to use this function instead of this function, so we don't have to actually calculate the normal matrix, but again, normal matrix a little bit later. Next, we are going to make a rotate function, void rotate f, actually rotate, and this will wait an angle. And actually I'm not going to make a rotate function, but I'm going to make a rotate x, a rotate y, and a rotate z function. I never like to use the rotate function as GL rotate f and then write the angle here and write the axis like 1, 0, 0. But instead I'm going to create a rotate x variable, a rotate x variable, a rotate y, and a rotate z variable. So I just like it better in this way. Of course, if you prefer this way, then feel free to do that. Alright, and the next two functions are actually to set the projection, which is one of the perspective functions, so void perspective, and it's waiting for the angle, the aspect ratio, so float aspect ratio. Actually, this is the aspect ratio, isn't it? The third parameter is the near and the far, so near and float far. You probably already recognize this function. This will be equal to the GLU perspective with the exact same parameters. As I said, we are trying to make it as close to the default as we can. The last one is the ortho. We haven't used that, although we are going to do that in the next tutorial. This is set up an orthographic projection. An orthographic projection is almost like the perspective projection, except the object far away don't seem smaller. That's basically the trick here. So it's a parallel projection. Like, just look it up on the internet if you don't know what orthographic projection is. This is, I said, the most important thing is far object don't get smaller. Okay, so it's waiting for the same parameter as GL ortho does, which is the left, the right, the top, actually the bottom first, then the top, then the near and the far. Near, far. It's defining basically a box instead of a whatever shape was it here. What was the name of that shape? Anyway, so it's defining a box, and this is equal to the GL ortho with the same parameters. Okay, that was it. I'm just going to make a few getters, although we rarely need to access directly to the matrices, but just in case if we need to access the matrices, then glm mat4 and get model matrix, and similarly we get the view matrix, the model view matrix, get model view matrix, get the model view projection matrix, get the projection matrix, and get the normal matrix. As I have said, normal. And these should be referenced so we can actually modify them if in some weird way we want to do that. But as I said, most of the time we don't want to do that. And actually, before I do that, we need a push matrix and a pop matrix. So void push matrix, and let me make the same kind of name as we had in the fixed functionality pop matrix. So these are of course equal to the GL push matrix and GL pop matrix. Alright, what else do we need? Of course, the only GLSL function which will be here is the update matrices. So update matrices. The update matrices will upload automatically the matrices to the GLSL shader which is currently on. So this should be an unsigned integer program ID. So it's waiting this program because of course we need the GL uniform to get GL uniform location to get the location of the matrix on the shader, and of course we need the program for that. And I'm pretty sure we have finished with everything. So let me just copy all of these stuff to the CPP file, and let's include the header. Perfect. Okay then, so let me just delete these, and this is matrices. Right, so what we need to do is actually set everything to the identity matrix. So let's see what matrices do we have. We have the model matrix, and we should actually push back a new matrix here, which is the identity matrix. So model matrix dot push back, and to get the identity matrix in GLM, so this OpenGL math library, we use the GLM math4 and the constructor with 1.0. This will get the identity matrix identity. We do the same thing with the view matrix. So right here, the view matrix. We do the same with the projection matrix. So everything we just set to identity. Projection matrix, and let's see. We set the current matrix mode to, I don't know, model, for example. So right here, current matrix equal to the model. Actually, this should be the capital model underscore matrix. You remember this is the enumeration value I create right here. So here, model matrix equals 0. Set the matrix is ready to true. There is no need to calculate anything yet. True. And let's make all of these to identity, because if we multiply identity matrix by identity matrix, we get identity matrix. So equals to GLM math4 1.0. And let me just copy and paste it. Model view projection matrix is equal, projection matrix is equal to identity matrix, and the normal matrix is equal to identity matrix, although this is a math-free, a three-dimensional matrix, because there is no need to translation in a normal matrix. Okay, the load identity will be fairly simple. I just get which is the current matrix. If the current matrix is equal to model underscore matrix or view matrix, we could actually set the model matrix and the view matrix separately, but I tend to use the load identity function to actually set both the model and the view matrix, the model view matrix, the identity. So I'm just going to make it as one. So if I just call it, if either the model or the view matrix is the current matrix, I set both of them to the identity. If you prefer to actually set them separately, then of course it's up to you. So then I just set the model matrix, and I get the top element. So model matrix dot size -1. This is how we get the top element from a vector. I set it back to the identity, so vector, not vector, matrix 4 and 1.0. So what I did here is basically create a new four-dimensional identity matrix and set the current matrix equal to that identity matrix. And I do the same thing with the view matrix. So right here, view matrix and the view matrix. Okay, I'm pretty sure this is it for the load identity, and we make an else. If not the model matrix or the view matrix were the current matrix, then it is definitely the projection matrix which should be the current. So let's make the projection matrix and get the actual element of the projection matrix, so size -1, so get the top element and set it to actual identity matrix, so GLM math4 1.0. Perfect, and I'm just going to set the matrices ready variable, matrices ready variable to false because we need to recalculate the matrix. The next one is okay, let me just copy this so we don't have syntax errors. I'm almost there. Projection, okay, and push matrix, pop matrix, view getter, and update. Okay, so the next step is to actually make the matrix mode variable. This will be fairly simple. If the I is equal to the model matrix, then set the current matrix to model matrix, then set the current matrix equal to model matrix, and else if the I is equal to the view matrix, then set it to view matrix, then set the current matrix equal to the view matrix, as if it is equal to the projection matrix, then surprisingly set it equal to the projection matrix. That was a simple function. It just set the current matrix. Let's see, the next one is the translate. So the translate will be relatively simple because the GLM library actually provides a translate function for us. We actually have to just create a translation matrix and multiply the current matrix by the translation matrix, because remember that the combining transformation equal to multiplying transformation matrix together. So if you want to get the current transformation, then I just combine together, so basically multiply together the current matrix with the transformation matrix. So we can get the transformation matrix by GLM translate and XYZ. It just creates a transformation matrix. It doesn't transform the current transformation, if you get what I say. It just basically translates from the origo. It doesn't get the other translations, the rotation and the scaling which we had earlier. So to get this, we just multiply this matrix with the current matrix. But what is the current matrix? It is determined by the matrix mode. So let me just put it into here. So if it is a model matrix, then I get the model matrix, which is get by this line right here. Model matrix, and multiply that by this transformation matrix right here, this translation matrix. So we now translated the current matrix by this translation. Else, if it is a view matrix, then I just get the view matrix again. I'm using the same technique right here, and just multiply together by the translation matrix. But in this case, we are multiplying by the negative translation. Why exactly? Because this is the camera. Remember, in the camera tutorial, when we do the translation, we actually translated with the negative amount of translation. So now the view matrix will pretty much act as if it were our camera. So we don't have to say that move everything back. We just say that we want to move the camera to the XYZ position, and this simple function will handle that, translating actually everything back. So I hope it's clear. So again, the same thing is happening when you walk forward 10 meters, then basically everything moves backward 10 meters. So that's why that negative sign is there. Okay, the scaling will be almost as simple as that. We have to use the scale function from the GLM library, and it's waiting for the angle, waiting for the XYZ. And by the way, I don't handle the translation for the projection matrix because there is no sense in translating the projection matrix. At least I don't find any kind of sense in translating projection matrix. So I'm just going to use the model and the view matrix to translate. Basically, the scaling the view matrix. Yeah, I think this is what scaling should be. The scaling with the same value will be almost the same as the previous line right here. So previous function right here. So I'm just copying to here, but instead of write x everywhere, so x, x, x. So it will change. It will not change the ratio of the object. Next one, rotate x. This will be a bit more interesting. although not too much because it's the same line, just we are using the rotate function right now. And this rotation function waits for the same parameter as the GL rotate f function in OpenGL. So for the angle, and then which axis do you want to rotate. So I'm just going to write, because this is the x rotation, I'm going to write 1 there, 0 there, and 0 there. By the way, without this f, the program doesn't compile well because it's thought that this is a double variable, and because of the templates and stuff, it doesn't actually compile without the f. Okay. And right here, I just do the same thing except with minus angle. The next one, rotate, actually this is rotate y and this is rotate z. I forget to modify it, so y and z. And this will be almost the same as the previous one, except the 1 will be at a different position. So let me just copy and paste. The 1 will be at the second column. As I said, it's a pretty simple class. You probably already bored to hell. Okay, the last one is almost the same as the first one, except the 1 is at the last position. The next one, perspective, again, will be pretty simple, and actually I don't find any sense in doing the perspective function to a model matrix or a view matrix. So what I'm going to do is just simple saying that whenever I call the perspective function, it will be made to the projection matrix, because I don't find sense in making to the view or the model matrix. So just get the current projection matrix, which I'm going to copy because that's quicker. So get the current projection matrix, and then I'm just going to use the perspective function right here. So perspective, and the perspective function waiting for the, first of all, the angle. So I'm just writing the angle, the aspect ratio, the near and the far planes, and there we go. That was it. I don't feel like putting the multiplication sign here, although I think this is how the OpenGL does it, because again, I don't find sense calling the perspective function and modifying the previous projection, basically. I just always create a new projection, so I'm not going to write the multiplication sign here. I hope it makes sense again. The next one is the ortho. That will be, again, just one line of code. This is GL ortho, GLM ortho, and just pass the parameters one after another. So left, right, bottom, top, near, far. Incredible. We have the orthographic projection. Push matrix might be a little bit more interesting because I haven't done that whenever I made the test, so I hope I know what to do. So let's see, the push matrix is actually creating a new matrix, which is exactly the same as the previous one, isn't it? So I'm just getting the current matrix mode, which can be done more easily by this. Yep, and I create a temporary matrix right here, so glm math4 and matrix, and this matrix will be equal to this model view matrix, so matrix equal to the model view matrix, and matrix equal the view matrix. So what I do here is basically setting it to the current matrix, else set it to the projection matrix equals the projection matrix, and get the last projection. Perfect, so I get the model, and now what we have to do is actually pushing back to the right matrix. I believe so, but I might be wrong. So if we were at the model view matrix, then I just use the model matrix that push back matrix. If I were at the view matrix, then I just call view matrix the push back matrix. And if I were at the projection matrix, then I just call projection matrix the push back matrix. I think this is how it should be. So what I'm doing is basically getting the current matrix and then multiplying it, so adding another matrix at the top of this matrix. I hope it makes sense, and I hope this is what the GL push matrix does. The pop matrix will be similar, except we are not pushing, we are popping. So GL pop, so we are using the pop back function, which is a predefined function for the vector to getting the last element, but we are only doing that if the size is greater than 1. It's greater than 1, because if the size is exactly 1, then we don't have matrix left, and we always want to have at least one matrix in the stack. So do the same thing. If view matrix size is greater than 1, then we are pop back. I think it's called pop back. Was it pop back or was it just simply pop? No, I think it was pop back. Projection matrix size is greater than 1, then we are going to pop the back. The pop back will pretty much just delete the last element. I hope this is how it looks like. Okay, we are finally in the simpler function. We are just returning with the current model matrix, which is this right here, the top of the model matrix stack. The next one just return the model view matrix, but actually we are not sure that the model view matrix is right. Are we? No, we are not sure if the model view matrix is right. So if matrix is ready, this was our boolean variable right here, which I forget to modify whenever we did something. So equal to false. We should probably copy this to everywhere, because when we modified one of the matrices, probably we screwed up the matrices which were already there. Copying. Translate a matrix mode is not modifying the matrix, is it? So when we do something modification, for example translating, then we have to recalculate the model view matrix, the model view projection matrix, and the normal matrix. Alright, so if the matrix is ready, then I just return with the model view matrix. Model view matrix. But if the matrix is not ready, then I just calculate the model view matrix. Model view matrix equals to view matrix times the model matrix. You remember the opposite order, so first the view and then the model, and then returning with the model view matrix. Or it would be a little nicer if the matrix is not ready, then we calculate the matrix, and then we just returning with the model view matrix, like that, exactly. Beautiful. We do something similar to the model view projection matrix, except we do one more matrix modification. You probably noticed that the equals, so the assignment operator and the multiplication operator are overloaded, so we don't really have to care. So model view projection, and then we first use the projection matrix. Oh, I don't write it right, did I? We have a stack. I almost forget. So we don't have model matrix and view matrix. We have this very ugly stuff right here, and same with the view matrix. Oh, so this is the view matrix. So we always just get the last element from the stack, and right here we do the same. So we get the model matrix and we get the view matrix, and we multiply them together, and we get the projection matrix, which we get similarly like the end of the vector. Projection matrix size -1. Okay, that was simple enough. I just multiply together the projection matrix, the view matrix, and the model matrix, and we have the model view projection matrix, which I just used to return with. The projection matrix is very simple because we have a stack. We don't need to calculate anything, so I just return with the last element of the projection matrix. Oops. And then finally we have the normal matrix, and it seems I can't avoid anymore the normal matrix subject. So you probably already know that whenever you rotate your object, the normal vector should be rotating with the object. So we could, in theory, use a model view projection matrix, but what is the problem? It works well until you're rotating object and scaling object, but what happens if you don't rotate and scale object, but instead of rotating and scaling object, you translate object? You can't really translate vectors because normal vectors should be at the center location. They are not translated, and by translating it, we are pretty much screwing them. So right here, I just started GIMP and show how the matrices actually look like. Let me make this black and smaller. So the matrix is a 4x4 matrix, as you probably know. Actually, I already showed you how the matrix mostly work in the first GLSL tutorial. Anyway, it has 4x4, so 4x4. That's about right. And then we have the scaling right here, so scale, and we have the rotation right here somewhere, so rotation, 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 and stuff like that. It has some other stuff beside, like the orthographic and the perspective projection, so it has projection right here, but the actual thing which does the translation is in the last line. So right here, last column actually, right here there is the translation. So the translation matrix is nothing else but you write how much do you want to translate on the x, how much do you want to translate on the y, and how much do you want to translate on the z axis. And you know, this is the transformation matrix. So you just write to the last column the x, y, z translation, and it will translate the vector. Now, if we just cut this down right here, we don't care about the translation. That could actually work if you scale uniformly. So until you are using only this scaling function, which scales at the same ratio, this one, which scales at the same ratio. But if you don't use that, you have to use the inverse transpose matrix, which you have to calculate. And actually, I'm not going to do that because I'm only going to use this scaling function. I'm not going to use not uniform scale. I'm going to use this scale, but I'm only going to use this scaling function. So by just cutting down these edges right here, so making pretty much a 3x3 matrix should solve the problem. It's rotating and scaling, but doesn't translating. Okay, so this is what the normal matrix is. It's pretty much the model view matrix, except only the 3x3 part, not the last row and not the last column. What else? And if you want to use non-uniform scaling, then just calculate the inverse transpose matrix, and that will be your normal matrix. So if I do the same kind of things, if the matrix is not ready, then I'm just going to calculate the normal matrix by get the model view matrix and cast it into a mat free. So mat free, and I just get the model view matrix. This is what it should be. And then I just return with the normal matrix. Okay, so the normal matrix is a 3x3 part of the model view projection matrix. I again don't go into the details of the mathematics behind it. Okay, finally the interesting function. It was all boring and copy-paste stuff, but finally we are almost there. So the update matrices will update the matrices in the GLSL shader. So how this function will going to work? Basically, first of all, we have to calculate the matrices if the matrices are not ready yet. So if not matrices ready, so pretty much using the same if statement right here, then we calculate the matrix right here, calculate matrices, and set the matrix ready to true, because then we are calculated, so we don't need to necessarily calculate again. Okay, so let me just calculate the model matrix, which is right here. The model view matrix, which is again copyable from here. And the last one is the normal matrix, which is just simple casting. Perfect. We have calculated the three matrices which we are going to need, and I'm going to send them to our shader. And now we are going to use a function called GL uniform matrix for FV. GL uniform matrix for FV. This is almost like the GL uniform. It's getting the first parameter is the uniform location. We are getting the uniform location and sending the matrix there. And V, because we are going to send a vertex, so an array, basically a vector of floating point number, which is a 4x4 matrix. This 4 is say that. So the first parameter is the location. So GL get uniform location. It should be already familiar to you at this function. The first parameter is the program ID, and the second parameter is the name of this matrix in our shader. I'm just going to call this matrix model matrix. So we have to create this named uniform variable right there on the shader, vertex shader. The next parameter is actually, it has more parameter a little bit. The next parameter is how many matrices do I want to send. So you can send an array of matrices. I only send one matrix. The next, if do you want to transpose this matrix, because as you probably know, the normal matrix in the computer store like this 1, 2, 3, and then 4, 5, 6, and then 7, 8, 9. While the OpenGL matrix store the matrices like 1, 2, 3, 4, and then 5, 6, and then 7, 8, 9. The transposing is an operation which basically turns this matrix into this matrix. So basically swapping the rows and the columns. That's what transposing does. And the next parameter is, do you want to transpose it? Now the thing with this GLM matrix that this is already storing the matrices like what OpenGL likes. So we are just passing GL false. We don't transpose this matrix, GL false. And the last parameter is just the address of the matrix which we want to send. So I'm just going to send the model matrix right here, the model matrix, and we can get the address for the model matrix by getting the address of the 0, 0 index. So address of 0, 0 index. So although there are a lot of array access operator right here, what this basically does is if you have a GLM mat4 matrix, then you get the address of the array of 16 floating point number by getting the address of the 0, 0 element. So right like this. The previous array access is just getting the current model view matrix, the current model matrix. Then let's do the same thing with the view matrix, and view matrix. Perfect. Then do the same with the projection matrix. So projection matrix, and projection matrix. Then do the same with the model view projection matrix. So model view projection matrix, model view projection matrix, which will be just the address of the model view projection matrix. Right. So address of the model view projection matrix. It is simple, right? Then the model view projection matrix. The previous one was the model view matrix. I said it wrong, I believe so. So I just write model view projection matrix. And the last one is the normal matrix, although we need to modify this one right here because it's a three-dimensional matrix, and I just call this normal matrix. And right here I just getting the address of the normal matrix. That was perfect. Simple enough. We have the matrices class. I hope we don't make too many mistakes in it. But we are not finished yet. We have to include this library. So let me just include it right here. Matrices.h. Don't forget that you have you have to include it before the GL header files, because the GLI needs to be included before the GL header files. And right here we included GLI. So just include it before any of the GL header file. Then I'm going to make a global matrix, so matrices, and I just call it peoplein because it is the transformation peoplein if you would like. So matrices, peoplein. Okay, and let's just go and change each of the functions. So let's go down and search for OpenGL function. We find one. This is the perspective, so we don't do anything else. Just use our perspective function with the actual exact same parameter. So let me just write it here, the exact same parameter. And I don't use matrix mode because, as you remember, we made the perspective right here, somewhere, right here, to affect the projection matrix, because there is no point in affecting other matrices with the perspective. So yeah, we pretty much done this part. Okay, almost there. We have a few more though. Let's go down and search for another matrix function. GL load identity, GL translate, and GL rotate. Perfect. So peoplein, and just use the load identity member function, and we don't need this load identity. Then let's translate. So peoplein dot translate, and let's translate. Okay, then use the people.rotate rotate y, and let's rotate. We're perfect. Although before I do all of this stuff, just to be on the safe side, I'm going to set the matrix mode. So matrix mode, well, or was it set matrix mode? Let me check. It was matrix mode. So just set the matrix mode equal to the GL model. Actually, no GL anymore. Just model matrix. Okay then. We have replaced all of these functions. Let's see if we find any more. Of course, we have a load identity here, so let's just load the identity here. So I'm just going to use peoplein.load identity. And let me think, do we need to change the matrix mode? I believe so, because right here these functions are actually using the camera. So I'm just going to change the matrix mode right here before the load identity. So peoplein.matrix mode, and I set just to view matrix, because now with this camera we are affecting the view matrix instead of the model matrix. So use the model matrix whenever you're translating a model, but whenever you want to translate the word, like with the camera, use the view matrix. So basically we are doing the camera stuff, then only when we do the camera stuff, use view matrix and use model matrix. We are going to pass as a parameter this peoplein into our camera, peoplein, and right here to the update camera as well. I will do that modification in a moment. Do we have any more of these matrix functions? No, we don't. So let's go into our lovely camera, and we are finished. And as soon as we finish the work here, so let me go to the camera.h and let's include it. So include matrices.h, and right here we are going to need in the control a matrix reference and called peoplein. As you remember, we have passed into the control and the update camera function these two stuff, so these two matrices. And let's go to the cpp file and let's do the modification on the change control function and the update. Alright, so now we have it. So let's change this rotate stuff. So first of all, we are rotating on the x, so rotate x and cam pitch, and then we are rotating peoplein, then we are rotating on the y. So let's just come here. Perfect. I don't use the minus sign right here because, as you remember, I use the minus sign right here in the matrix, the rotate, whenever I rotated the view matrix. As you can see, I have used this minus sign, minus angle right here, so I don't have to use it here. So I just delete this GL rotate stuff, and one last function is remaining before we can go debugging, which is this. So just pass the location.x, location.y, and location.z. Yes, there we go. Actually, no, we have to modify the shader too. Okay, alrighty then, let's open the shaders, all of them. Do we have any more shader? We should have a fragment shader. Yeah, right here. Okay, we have 4 shader, and actually we only need to modify the vertex shaders, I believe so. So let's create all of those uniform variables. So uniform mat4, which is a 4-dimensional matrix, and I call this model matrix. And we have a view matrix, and we have a model view matrix, and we have a model view projection matrix, and we have a matrix 3 called normal matrix. I believe we had these 5, but we can go back and check. Right here at the bottom, we created the model matrix, the view matrix, the projection. No, we didn't create the projection matrix. Okay, let's just create the projection matrix, and then we have all of the necessary matrices. Projection matrix. There we go. Okay, so let me just change this built-in GL model view projection matrix to our own class, which is the model view projection matrix. Let's change the GL normal matrix to our own class, which is the normal matrix. And here we have another matrix, the model view matrix. Let's change it our model view matrix. And we are almost finished. We only have to copy these uniform variables right here to the other fragment shader, which is rendering the quad. And let's just change this model view projection matrix with our model view projection matrix. Whew, I believe so we are finished. So let me try to compile it. Oops, that doesn't seem too right. Okay, there is no matching function to rotate y, and y is no such function. We will check rotate y. I see such function. Oh, of course. Let's go back to the camera. And this is not rotate, this is translate. So people will translate, of course. Okay, and then let's go to the matrices at CPP line 41. So 41. And on line 41 we have an I right here. Oh crap, I wrote I everywhere. That could take a while to fix. So this is the current matrix, not the I. The I was here, just I copied it to everywhere. So copy, actually paste, technically paste. But that should eliminate a lot of problem because most of the error were from I wrote I instead of current matrix. A little embarrassing, but oh well, I survive. I. Really, the copy and paste is the most dangerous thing you can possibly do in programming because you're multiplying the errors by every copy and paste. Okay, I didn't see any more, so let's just check. A little bit more manageable, 119. Projection matrix, 136. Yeah, another copy and paste error. Who thought? 157. Yeah, this is projection matrix, not projection. 163. The same error because, you know, copy and paste. 170. Of course we are returning mat free because the normal matrix is a matrix free. So let me just rewrite that. 180, copy and paste error. 182, matrix, of course, because this was called matrices ready, not matrix ready. And that should, let me see, come on. That's right, no error. Now we only need to worry about the shaders. What does the shader say? Nothing. And we get nothing. Good. We screwed up somewhere and I have no idea where. I have an idea where we screwed up. We didn't send the actual data. We should call this update matrices function every time we draw something. So let me just go into here before we draw. Every time we just say people in, if we can type it right, dot the update matrices, and let's just get the ID for the main shader. Main shader, actually right here it is. Get program ID. And again, we do the same thing right here when we draw the other quad. So right here. And this time we are going to use the quad shader. And let's see. We put it right here after we use the shader. And let's see. I hope this was the error, because if not, then I can debug a lot of stuff. Yeah. Oh, that's good. That's a good news. It was the error. So as you can see, we get back the same program we had before, and everything worked the same as before, and I hope everything is working as it should be. And yeah, that's pretty much conclude the tutorial. We have our first OpenGL 3.2 plus program. Actually, I write it here because I'm so excited. First OpenGL 3.2 plus program. Right there. Okay, so we have our first OpenGL 3.2. I actually checked all of the GL function with the OpenGL 4.0 specification, and we didn't use any of the outdated function according to the OpenGL 4.0 guide in the CPP file. So I'm really happy for that. Finally, we can actually so this was a free, by the way, I wanted to introduce this at the beginning. So this was a free outdated function which I have showed you throughout the OpenGL series. The immediate mode was oops, what button was that? Was replaced by GLSL. The fixed people int was replaced by vertex buffer object, and finally the building matrix was replaced by GLM. Oh, finally. So we can actually go into the more interesting stuff in the next tutorial, where we look at the post-processing in GLSL. But till then, thank you for watching, and